lot of people there. All of that is going to contribute to the noise and make my decision making process even more challenging. And in the fourth image here, we see that there are highly zoomed in images. So while you may be able to see the scratch or the tear over here, you may not be able to understand completely what part it is coming from. So all of these complexities, all of these challenges make this problem a difficult one. So let me give you two examples of two different sets of images that we work with. So here we see set one of images. This is a car and we are viewing it from the front right corner. This is a more right view of the car and we see that there is a damage over here. So again, in this second example, we see another car. And again, here we are viewing this from the like rear left corner. Whereas in this image, we are trying to view in or trying to zoom in on this damage which is there. So if what my goal is that I have to find that these damage instances that are there across these two images for the same car is in fact the same damage instance. While it is very easy for a human to understand that, for a machine to understand that, there has to be some visual characteristics which match across images. So my goal is to match these two pairs of images. And the problem that we have faced is that there is a high angular and high scale variation as is observed from these two images. Now, what have we done in order to make this solution? We have 6 modules over here. So the first module is identifying the segmentation maps of the vehicle parts that are there. So we have a vehicle parts, an image of a car, and we have different vehicle parts in that. We want to take a pixel level call at what pixel belongs to which part. And I think it'll be clear to you when you see the results. The next one here is a part classification refinement. It is more like a post-processing module wherein we are trying to clear a confusion in case there is some misclassification from the part segmentation. And we do that because parts are indeed a very important feature for us to have a proper decision. For example, if I'm looking at a frontal image of a car and I see two headlights, and my part segmentation module has called both of them as right and both of them as just headlights, then I need to check which is the left headlight and which is the right headlight. So those kind of things we address in the part classification refinement. And then we have a vehicle damage segmentation, wherein we are taking a call at the damage level to understand what are the damages on the vehicle. And once we have done that, we are doing a damage to part association. For example, let's say the left door has a dent. So the left door has a dent in one image. The left door has a dent in another image of the same set as well. So if we could use this information, then we can arrive at possible candidates for duplicate instances. So now from these possible candidates, we have to ascertain whether in fact these physical damages are actual duplicate instances or not. And this is where we are using a combination of computer vision geometry to figure out whether these two instances, a pair of instances are the same instance or not. And then we do a final cost estimation to arrive at a decision. So let's go over these modules one by one. Yeah. So the vehicle part segmentation here that you see, we are taking a call at the pixel level. So this is a segmented output, and many of us may be familiar with the segmentation techniques that are there in the state of the art. The one that we have used here is Deep Lab V3 architecture. And again here, so these two images are this image of the same car, but from very different angles and different scale levels. The first step here is to find out the segmentation outputs of the vehicle parts. And now here we see that this particular red region that is there, which is the right fender of a car, has a dent in it. And here again, we see that the right fender of a car has a dent in it. So what we have tried to do here is we have looked for anchor parts. This is a coin that we have termed in our paper. And the term anchor part refers to the vehicle parts which are used to find relative location of the damage instances in the vehicle. They are chosen keeping a few factors in mind. So they should be having distinct visual characteristics for reliable segmentation. Further, they should be small and compact, so that the centroid, which we will use further, as you will see. So the centroid is a good representation of the entire part. If an anchor part is chosen, for example, this part over here, which is very long in nature, the variance of the rest of the points from the centroid will be really high, and it cannot be considered a good approximation of the centroid, of the entire part. So for our case, headlights and wheels, after careful experimentation, has been found out to be good parts, reliable parts, which give us good results. And again, we have another term here, which is known as a front-back identifiers. And these front-back identifiers are nothing but indicative of whether it's a front view or whether it's a back view of the car. So here you see this green thing, this green part, which is the hood, is a front identifier, whereas in the back there's the deck lid, which can be used as a back identifier. Now, in the next module, we had a vehicle damage segmentation module. So here again, what are we doing? We are finding out the damage segmentation map of this dent that we see over here, and this dent in the second image of the same set that we see over here. Now, what are we trying to do? We need to do a damage to part association that was seen in the block diagram before. So now we have the different vehicle parts, and we have the damage instances here, and the same we have over here. So what are we trying to leverage? We are trying to leverage the centroids of these parts, the centroids of the lamp, the centroid of the vehicle, the wheel, and the centroid of the damage over here. And the same we try to find out the corresponding points in image number 2. And we know that these are the same instances. And can we use this information to actually ascertain that these in fact are the same instances? So let's recap the steps that we saw before. This is our image 1 and image 2 of the same set, which represents, the same object, the same card that we are trying to identify. And our objective is to find out that this damage over here and this damage over here is the same damage. So we do a part segmentation of it, where we have got the part outputs. Then we do a damage segmentation of it, where we are getting the damage segmentation map. And then we are trying to find out the centroids of the damage, the headlight over here and the wheel over here. And same for here. We are trying to find out the damage centroid over here, the headlight over here, and the wheel over here. And we see that it makes an angle phi1 over here, phi2 over here. So let's take this, and we have used these 3 points. So DC1 is the damage centroid for the first image, the headlight centroid for the first image, and WC1 is the wheel centroid for the first image. This is the angle which it makes. And from these 3 points, we are able to find out a 4th point, which gives us this parallelogram, which is our 4-point geometry. And we do the same process for our image number 2, and we get a 4-point geometry over here as well. And the same conventions for naming these points apply here. Now, these two are very different planes. So this angular comparison is not an apple to apple comparison. So what can we do to make these planes the same, so that we can in fact have a very good comparison? We take this image and try to transform it to this plane through homographic transformation. We are doing a homographic transformation and we get a homographic matrix, and we use that matrix on image 2 to transform the entire image to that plane. When we do that, once we have done that, we again find out the damaged centroids, the lamp centroids, and the vein centroids. So now you see that this is phi 2t, which is the angle in between these lines of the transformed image. So this is our parallelogram that we have got, and this is what we had before. So now this and this, these two are comparable because they are in the same plane. So what we do is we find out the angular difference in between these two. And the angular difference is denoted by the absolute value of the difference of these two angles. And it is denoted by D. And this is how we devise our similarity index. Now, the similarity index is an indicator of of the resemblance of these two damage instances. So, if my similarity index is high, I can ascertain with greater confidence that these two damage instances are in fact the same damage instances.
So sorry to interrupt. So I request you to probably wrap up your presentation in next 2-3 minutes.
Sure. I'm almost towards the end, and the evaluation results are for the different modules: vehicle path segmentation, damage segmentation, and duplicate damage instance identification. So here we have used the open source Pascal parts dataset. We have class labels of 24 parts, and the metric that we are using is validation MIOU, which has come around to 0.71. For the damage segmentation, again, we have hand annotated points and hand annotated data sets. And these are the class labels, different kind of damages that we are trying to find out. And this is the validation MIOU that we have got. For the duplicate instance identification, we have around 1,000 pairs of images which have been annotated to be labeled to be duplicate or non-duplicate pairs. So this is a pairwise comparison. And for the elaborated details, we go to table 2, wherein we are comparing it with the standard feature matching methods, SIFT, ASIFT, SURF, and ORB. So if you see here in this table, our proposed solution gives us an F1 score of 0.81, which is higher than all the previous image matching methods that we have seen. Concluding the presentation, the novelty in our approaches that we have a similarity score, similarity index to quantify similar pair of instances. We are using anchor parts and identifiers which are internal to the image for reliable computation of similarity. We have a scalable solution. We have actually deployed the solution, and it's portable across open source platforms. It is reusable in different domains, which means that if in the field of, let's say, 3D reconstruction, or maybe in the field of sports, if we have to do third umpiring, things like that, the solution is scalable with the provided we have some reference parts over there. And it is very easy to explain to the stakeholders because it's quite an intuitive solution, and we can actually represent our solution with the help of the damage to part association that we saw. So that was my time, and thank you for listening patiently, and I think I'm open to questions now.
Thank you. So we welcome questions from any participants, so they can unmute themselves and ask. Okay, then probably I have a questions. Yeah, so I guess someone has question, please.
Hello. Am I audible? I'm not able to.
Yeah, sure. So I think, yes, I thought someone is asking. So thanks for a very nice presentation. So you are showing the result and compared with some of the popular techniques, but have you also compared with some kind of state-of-the-art papers?
So the state of the art in this case, where people are trying out different ways to arrive at something like this. The state of the art, if you ask me, there are some object co-detection, object co-segmentation methods that are there. However, it would not be comparable with our data set. If you see here, our data set has very high angular variation. In the most many of the object segmentation data sets, the angular variation, the scale variation is constrained. It is in a it's on open source data set, and it is on in a constrained environment. Whereas our problem is many in a totally unconstrained environment, and that is why it is important to have some kind of reference, some kind of real world reference within the object. So, although we are while we are trying to assess different deep learning techniques, different Siamese network kind of techniques in order to find out the similarities, but so far this is the best result that we have got.
So I guess there is a question by Ankur Bhatia. So I request the volunteer to unmute him.
Yeah. So, hi. Thank
Hi.
you for the nice talk. So, in one of the images, you showed that there were detection of the centroids from the front wheel as well as from the rear wheel. So
Mhm.
there can be many centroids that can come up from the algorithm. So how are you
Yes.
basically finding out which angle or between which centroids you have to find that particular angle to match?
Right. Thanks, Kush. I think it was a good question. So if you see here, there are two different wheels and two different centroids, right? So we do a kind of screening to find out what are the commonalities in this. So I see if I have, I'm of course going to be taking a three or a triplet of centroids. So I can consider this to be redundant in this case and take a 1, 2, 3 and 1, 2, 3 of this, because when we are doing the segmentation we also know that which part it is coming from. So I am not going to be taking the centroid of a part which is not present here only. So I'm going to be taking the ones which are present here, and only then it would be a proper comparison, right? So that is the answer. I hope I have clarified.
Okay, so thank you everyone.
So
I guess this is the, I think we have this much time only for this paper. So I request the next speaker to come. So the next speaker is Susmita. Is she here?
Sumit has one question. He has raised his hand. So, do you have the time?
Okay, we can have a quick question. Yeah, please.
Sumit, please unmute yourself.
Good morning, all the members. This is Dr. Sumit. Adrita, I have actually one question from your presentation. That
Yes,
if
please.
we finding when we finding the centroid, if we
Mhm.
have true positive or false positive, or true negative or false negative, then
Mhm.
how we will handle such scenarios?
So true positive and false positive for which module are you talking? Are you talking about the part detection module?
Yeah, yes, I am asking for the same.
Okay. So the assumption here is that our part detection has to be really good, and if because if this is that is the basis of the entire entire solution. If the part is, for example, as I had said, if there is a a left right confusion, for example, my headlight over here, if it is called a left headlight instead of a right, which it actually is, it may lead to a wrong association. So we do a lot of post processing in order to maintain that this is in fact we use positional references to maintain that these are in fact the paths that are there, and side by side we also try to improve our deep learning models to properly identify the paths.
Okay, perfect. Thank you for answering.
So thank you so
Thanks.
much, Adrita, and thank you so much everyone for asking questions. Okay, so now I request Susmita to present her paper. So I request volunteer to make her presenter.
Yes, sir.
Adrita, can you please close your presentation?
I have closed my.
Hi everyone, am I audible?
Yes, Susmita, we can hear you. So please share your presentation.
Yeah, just a minute.
So Susmita, you have so we have 20 minutes for your paper. So please try to cover your presentation in 17 minutes, so that 17 to 18 minutes, so that we can have question in next 2 minutes.
Yeah, is my screen visible?
Yes, it is.
Please get started. Thanks.
Okay. So good morning everyone. So okay, it's afternoon. Good afternoon everyone. So today we are here to present our paper, Focused Questions and Answer Generation by Key Content Selection. So my name is Sushmita. Along with me, I have my colleague Ravi Kiran, who is also going to, we both are going to present this paper. So in this paper, we are targeting the age-old puzzle of automatic question and answer generation. So we all know that automatic question and answer generation aims to generate questions and answers within a given piece of text. So you input a given piece of text and then it generates questions and answers, but the answers lies within the text or the given substance of the text. So here we are targeting mostly WH type questions or the reading comprehension type questions, because these are the most popular kind of questions. And the thing is that a lot of work has been done in this section, like automatic question and answer generation, for a long time. So what makes us different is that we have here put an effort to make it more human-like or more natural. By that I mean is that when a teacher asks questions to its student, he might frame the same question different way and ask it to different students. So it becomes easier to track if the question if the student is especially for online questions in this COVID situation, where this online tutorials and assessment has become very popular. So if we have different questions, differently framed questions pertaining to the same answer, then it becomes very easier and also very interactive for both the students and the teachers. So what the main essence is that we have targeted diverse sequence generation from the same piece of text. So we have 3 questions generated on which has the same answer. So this is mostly our work. So it has a lot of potential in the education as well as the publishing industry, as I said. So it can be used in chatbots, it can be used in online tests, it can be used in quizzes and self-assessment as well. So how did we do this? So for training our model, we have used the Stanford question and answer generation data set, which is the Squad 2.0. So this data set mostly has a piece of text, its corresponding questions and its answers. So it's a huge data set. It has almost like 1 lakh source and target pairs. And we have split our data set in this format as shown in the slide for training, validation, and test respectively. So along with the data set, we have also used a lot of other features which will enrich our model. For example, we fed to the model some lexical features. For example, the parts of speech like verb, adverbs, nouns, pronouns, and others like parts of speech. We have fed the named entities, as in like place, geopolitical entities, then a person, then maybe a date, because these are very important part in a sentence, right? Because and the word case features also. So if it is small letters, if it's in big letters, so if it is in big letters or it starts with a big letter, it might be some important information. So the United States, something like that. So Along with the text and the lexical features, we also feed the answer to the model. So how do we select the answer? For selecting the answer, we use Spaces neural entity selection algorithm mostly. And then we used a biotagging sequence. By biotagging sequence, I mean that when there's an answer, the start of the answer is denoted as B, and I is the continuation of the answer. And then after that, the other part of the sentence, which is not contributing anything towards the answer, is tagged as O. So we are feeding mainly the data set, the lexical features, and the target answer. So after that, here is basically the model architecture that we have used. We can see that this is a like traditional this encoder decoder model. So mostly the work that we have done is on the focus generation part. So we have introduced a new module called the focus generator module, which actually helps us in generate diversified questions. So after this, I would like to pass on to my colleague Ravi. Ravi, are you there?
Yeah, Sushmita, thank you.
Yeah.
Yeah. Hi, everyone. I'm Ravi Kiran. So I'll be talking about the model architecture. Sushmita, you can go back to the previous slide, please. Yeah, thank you. So the architecture is mainly divided into like two major modules, the focus module and the encoder decoder module. So in the focus module, we have a focus generator along with the focus sets. So I'll talk about what we are actually doing in the focus generator and how we are actually selecting the focus sets to generate diverse questions. Yeah, Sushmita, you can move to the next. Okay, the focus generator model is a model which actually generates a set of different focus words, or we can say keywords or the important words, okay, based on the information available in the input sentence. Okay, so we actually select these focus words or the keywords using NES algorithm, which actually distracts stop words and other unused, other not usable words and special characters, and selects only key information from the sentences. Okay, the main scope of this is to create a difficulty factor for the questions. It's like there are three questions focused on the same answer, and the question with the least amount of information or the keywords in it is labeled as hard, and the question which has more keywords or more information in it is labeled as easy. So it is more the information in the question, more easier to answer that question. Okay, you can move to the next slide. Okay, so how are we dividing this or selecting these focus words? Okay, basically what we are doing is we are splitting the sentence into three groups. And in one group, so in the first focus set F1, say F1, we are using only one group to create the focus words or to select the keywords from that group. And in the group 2, we are using, so in the set F2, we are using two groups. And similarly in set F3, we are using all the groups or all the information available in the sentence. Sushmita, you can go on. So as you can see here, this is an example of a input text. You can see input text: medical, surgical, nursing is a specialty area of practice, and the answer is medical, surgical, nursing. So this is the first focus set. Okay, in the first focus set, I have selected some of the focus words or the keywords. First group is area nursing patient adolescent's life, and the second is specialty area practice, and the third is specialty area. You can see in the F2 group, we have more information. In the F3 group, we have more information. So what we actually do here is amount of information in F2 is very less and F3 is very high. So we are trying to select only one part from F1, one part from F2, and one part from F3 to create questions. So we do it. We are actually selecting this based on the model error, model error or the model loss. Like, yeah, Sushmita, you can go. So we have used a basic encoder decoder model with bi-directional GRU units, and we are actually using 256 hidden states, for encoder and 512 hidden space for GRU decoder, and we are using a 300 dimension word embedding from Globe, and we have limited our vocabulary to 20,000 keywords. Yeah, you can go to the next slide. So this is the basic, this is one of the examples like how we are trying to create diverse questions using our model. You can see this is the original sentence. Clinical cardiac electrophysiology is a branch of medical specialty of cardiology, and answer is clinical cardiac electrophysiology. So you can see 3 questions which are focused on the same answer, but the amount of information in them is very different. So or they are diverse or they are rephrased differently. So if you can see the first question, it is using only the information from the focus set F1 to create a question, which is logically correct and focused on the same answer. And if you can see the second question, it is using the information provided in the focus 2, and it is logically correct and it is focused on the same answer. Similarly, the third question, it is using only the information provided from the focus set F3, and it is focused on the same answer. So here we are actually controlling the amount of information to be provided in this sentence with the scope of adding a difficulty factor to the questions itself. So this way we can create diverse questions. Shushmita, go ahead. Yeah, this is one of the more example, one of the another example, like similar example. So here also we are using the same logic. You can see the questions are logically correct, and all the questions are focusing on the same answer, but the information used in the question is limited to the focus sets F1. So this question is bound to use only the information from the F1 set, the second question from the F2 set, the third question from the F3 sets. So we are the main difference in our model is we are actually generating diverse questions, not only one question. Yeah, Sushmita, you can go ahead. So this is the comparison chart. Okay, so these are the different methods. So we are actually using Blue's 4 score, which uses 4 to compare from the result and the reference sentence, and these are the similar papers who have been working on the same diverse sequence generation, not just question generation, but diverse question generation, more than one question. So you can see our model has a Blue score of 16.5. It is not high, but in terms of speed, like we are like faster, and we have got a better score. Yeah, Shushmita, you can go ahead.
Less training time by 20%.
Yeah, Shushmita, you can go ahead. And future work, we are trying to customize the architectures like BERT and GPT to this task. So we are currently doing that, and so the features are the pure stagger, NER, and keyword features are very important to generate the question. So the more accurate pure staggers or NER we use, the more accurate the model will be, because the model will try to learn more syntactical information from the language, and using more training data. So obviously using more training data, we can increase the accuracy. So we are currently working on it, and the limitation is we don't actually have a way to justify or evaluate how diverse our questions are. And like similarly, like all the models, our models tend to fail on complex sentences, like which has multiple subjects, or which has multiple noun phrases. Yeah, Sushmita, you can go ahead. Yeah, any questions?
Okay, so thank you everyone. So thank you Ravi, Kiran, and Susmita. So any questions from audience? So I guess Sumit has some. So I request volunteer to unmute him.
Am I audible to everyone?
Yeah.
I have two small questions.
Sure, sure.
What I actually perceived from this presentation is
Yeah.
that let's suppose I ask something in Hindi that तुमने आज क्या खाया है,
Okay.
or in English it is what today you eat. Let's
What?
suppose I
Yeah.
will rephrase it, तुमने क्या खाया है आज, what you eat today. So these two are basically the different questions, but the answer for these two questions are same.
Well, we are only focusing on one language, English, and your as per your question, it is in different languages.
No. See, I understand that your work is specifically for the English language.
Yeah.
But my question is actually 2 point. One is that how it is different from the paraphrasing, and second thing is if the similar approach what you devise right now, if I apply for the regional languages such as
Yeah.
Hindi, Kannada, or anybody else, then I think it might fail or the complexity will increase.
See, as I said that we completely focus on the amount of information in the sentence. Okay, no matter the language. So to when you say it might fail on different languages, because like the understanding of the syntactical or the natural language is not only dependent on the model, it also dependent on the word vectors we are using and parts of speech tags we are using. So if you want to train on a Hindi or different language, we have to use Hindi word vectors and Hindi parts of speech tags. So the model remains the same.
And what about the paraphrasing?
Yeah, paraphrasing is like, when you say paraphrasing, it is actually using all the information in the sentence, but it is phrasing is differently. Okay, our model is like, if when I say your question, say, I'm hungry now and I'm trying to eat something, like, I'm trying to eat something. So it actually uses this information to, split. Like, in one question, it will just ask you about the hungry. In other question, it will trying to add, like, what you're trying to eat. Like, so it is actually controlling the information, not only using all the information in the text to paraphrase.
So, Sumit, so just to answer your question, we are not only paraphrasing. So you see the two questions, which is a branch of the medical specialty of cardiology, and which is a branch of the medical specialty of cardiology and is concerned with the study of rhythm or disorders of the heart. So the amount of information, I mean to say, it's not, is it exactly just paraphrasing? It is also adding some extra information which is valuable. So it's not only that what did you eat and were you hungry. So it's not only framing the questions differently, but also adding and removing informations.
Okay, some
On the
intelligent
keywords.
portion is
Yeah.
also there in this algorithm. Okay, fine. Thank you. Fine.
Yeah.
I'm saying that some intelligent portion is also there in your algorithm.
Yeah.
Yes. Fine. Thank you.
Yeah. I answered your question, right?
Yes, perfect.
Okay, thanks.
Oh.
Thanks, Susmita. Thanks, Sumit. So any last questions? Okay, if not, then let me thank speaker. And I request Pratibha to present her paper. So volunteer, please make her presenter.
Thank you.
Yes, sir.
Hello, am I audible?
Yeah, Pratibha, we can hear you. You may get started.
Okay, should I start now?
Yeah, please.
Okay, good afternoon all. My name is Pratibha. I'm going to present my paper, which is multivariate adaptive Gaussian mixture. 1 second. Yes, Gaussian mixture for scene level anomaly modeling. This work was done under supervision of Dr. Mukesh Saini. Yeah, I will be following the following table of contents. First, introduction, motivation, challenges. Then I will discuss the related literature, dataset. Then I will discuss the proposed work, experimental results, and finally the conclusion and future work. So what is anomaly detection? Anomaly detection refers to the problem of finding patterns in data that do not conform the expected behavior. Here in the diagram, we can see two bigger clusters, N1 and N2, and there are some smaller clusters and standalone points, O1, O2, O3, that are not lying with the majority of the data points, which are in N1 and N2. So these O1, O2, O3 are anomaly points. Now let's see the motivation behind this work. There are two examples shown in the slide. First is anomaly detection in the farmland. A drone is taking the video of the farmland and generating an anomaly map. The red color suggests the abnormality and green suggests the normal. So farmer can look this map and directly go to the farmland and take the necessary action. He or she does not need to go manually and check every area in the farm. Thus, it helps in the automated monitoring. In the second example, which is of city surveillance, automated anomaly detection can generate an alarm for suspicious situation. So a security operator does not need to look every monitor continuously. He can directly look the alarming monitor, and thus it saves the time as well as increases the performance. There are some challenges in anomaly modeling. First is high intra-class variance. In the diagram, all the examples are showing the anomaly classes, and the data was recorded at a reception area of an educational institute. First is birthday celebration, second is fighting, and here we have aerobics, here crowd, and suspicious object and running. All this activity lies very far away from each other in the feature space. So this is the high intra-class within the anomaly class. So one single class for abnormality does not work. You will have to train multiple classes for each type of abnormality. So it will only work for when your aim is to train a model for some fixed classes of anomaly. That cannot be generalized for the task where your task is to find in general suspicious situation. Another challenge is dataset availability. Abnormality is a rare phenomena, so getting abnormal data is not easy. The other solution may be that train your model with using just normal data, and whatever is not belonging to that model is abnormal. But the problem is that getting all type of normal data is also not practically infeasible. And labeling such a vast volume of video data in real life is not easy. Another challenge is often vague boundary between normal and abnormal classes. Often the labeling becomes subjective phenomena. Another challenge is context dependency with video data. We have generally spatial and temporal context associated. In the first row, we have a running event. In first diagram, it is an abnormal situation, whereas in the next, it is normal. The same event becomes different because of the associated spatial context. Similarly, with this fighting event. In the third example, we have a periodic data. At N1, the lower value is normal, whereas the same lower value at O1 becomes abnormal because of the associated periodic context. So we observe that knowing the context becomes essential, or modeling the context becomes necessary in order to classify correctly. Sometimes the associated context is hidden. We don't know in the prior, so it becomes a challenge. Another issue is concept drift. In many domains, the behavior of data distribution keeps changing over time. Thus, an event which is abnormal today may not be abnormal in the future. It may be a new normal. For example, in the first diagram, which was taken before lockdown, the crowded road is normal situation at that time, and a vacant road is abnormal during those time. In the second diagram, we have during the lockdown picture. So this vacant road becomes a new normal. So if you use a static model which was trained before lockdown, so that model will classify vacant road as abnormal for this situation. But that same model, if you keep using that, it will again classify this vacant road as abnormal. So raising false alarm. Hence, the model should be continuously learning. Otherwise, it will raise the false alarms. Now coming to literature and dataset, the initial approaches for video anomaly detection were based on tracking-based method. Generally, the optical flow-based and GMM-based tracking were used to extract tracks, and then clustering-based approaches or one-class SVM-based approaches were used to analyze the tracks and classify the unusual tracks as abnormal one. The limitation with these approaches is that it was computationally costly to keep track of each and every object coming into the scene. Another was that the appearance-based anomaly may go undetected because it was only considering the motion information. Also, this method tends to fail when used for crowded real-world scene where the shading, blurring often occurs. The another approaches were traditional shallow methods, which was using handcrafted features such as 3D gradient, VGG-based appearance feature, HOG features, MDT features, and the approaches that were used at a time were logistic regression-based method, nearest neighbor method. And the limitation with that approaches was that it was using the short-term temporal context, that is the duration of training data, which was just limited up to 2 to 5 minutes. And also, since the model was static, so it was neglecting the concept drift. The state-of-the-art works are using deep learning and they are reconstruction-based method. So in this method, we have some delta K frames given to the network and it reconstructs the current frame IT. It is compared against the ground truth and a reconstruction error map is generated. So the idea behind this reconstruction network is that this network learns well to reconstruct the normal data, which is in majority of the amount, and it doesn't learn to reconstruct the abnormal, which is in less amount. So it produces high reconstruction error for abnormal points. So keeping a threshold on reconstruction error can be sufficient for classifying. Autoencoder and variant of autoencoders were used at the reconstruction network. It was used in both in semi-supervised and unsupervised fashion. The limitation with this approach is that it is offline training, also considering the short-term temporal context. And it was also giving a problem of narrow regularity score, that is the less difference in reconstruction error of normal and abnormal for some of the data. This narrow regularity score problem was tackled by the prediction-based methods. Mainly the GAN were used for prediction network, and instead of reconstructing, it was predicting the next frame, and a prediction error map was being generated. The limitation with this approach is that it is also a static approach, not adaptive. This is some sample frames from the public available video dataset. First column is UCSD dataset. The presence of cart is showing abnormality. Here people are throwing bag, that is abnormal situation in Shanghai Tech. And this column suggests the frames from subway entrance dataset. This was recorded in the subway. There a vehicle comes and people go from right to left to catch the vehicle. And the authors manually come from left to right to create anomaly as wrong direction. In this table, I compare the public dataset with our dataset on the length, location, and continuity. The location means the data is recorded at single location or multiple location. Continuity means recorded in one go or multiple chunks. So we see that all these data set is not suitable for our purpose, where the location should be single and it should be in continuity in order to develop a scene level adaptive model. The subway entrance and exit data set is useful for our purpose because it is recorded at single location and in one go. But again, the labeling done for this data set is done as fixed anomaly only. The sudden emergence of crowd is not considered as abnormal by the authors for this dataset. Anyhow, we have used this dataset. Our data is a 10 hours long dataset. It is recorded at a reception area of an educational institute. For labeling, we consider the interesting events from a surveillance perspective, and we hire some of the security guard posted there to label, and we take the collective view. This is some sample frame from our dataset. The first row suggests the intensity variation from morning to night. And in the second row, we have some examples of abnormal samples like aerobics, abnormal object, some suspicious object, sudden crowd emergence, etc. Now I'll discuss the proposed framework. We have a CCTV, video streaming is coming from there. We take a video event and compute semantic attributes as well as low-level attributes. We get a combined event representation. Then we have a adaptive multivariate GMM framework. that event goes to this framework. It adapts the parameter according to this event, and that event is labeled as normal and abnormal by the framework. There are two key tasks in the proposed framework. First is scene representation, and other is adaptive scene learning. Let's look the scene representation. We have delta E event, which is the frames in delta T duration stacked together. We compute low level features as angle and magnitude information at its pixel. We compute a weighted histogram of angles with patchwise, and we concatenate all the histogram from each patch to get a single histogram. We compute semantic feature as person, animal, and vehicle count using YOLO object detector in delta E event, and we concatenate the both of the features to get a single representation. Now coming to scene learning. Initially in the mixture there is no Gaussian. So at arrival of first event, we start a new Gaussian as the mean as the event representator, and the variance is kept high variance value, which was initially calculated using some data. And we assign a initial weight as 0.005, it is fixed. After this event, when a new event comes, we test it against the existing Gaussian in the mixture, if it belongs to or not. So how to check belongingness in the Gaussian? For 1D Gaussian, 95% population lies within plus minus 2 sigma. So if a sample is inside plus minus 2 sigma, then we can consider it is an inlier. And z-score distance gives this distance of a point from the mean. For multivariate case, we have Mahalanobis distance, which gives the same distance for multivariate case. But this sigma rule changes for multivariate case. Like to accommodate same 95% of the volume, the 2 sigma may change to 5 sigma. For our case, we have theta Mahalanobis, like threshold on the Mahalanobis distance is 5. So the Mahalanobis distance, if it is a less than equal to 5, then it is a belonging to that Gaussian, otherwise it is not belonging to that Gaussian. So after this matching, we update the parameters of the mixture. The weight of each Gaussian is updated using this following equation. The alpha is a weight update rate, and m is the either 1 or 0, m for the matched Gaussian and 0 for the non-matched. W is the previous weight of that Gaussian. And we update mean and variance of the matched Gaussian only using this equation. This is considering the previous parameters as well. And we have a gamma t, which is contribution factor, and it is inversely proportional to the Mahalanobis distance. Means the point which is far from the mean should contribute less. After updating the parameters of the mixture, we label that sample as the status of the matched Gaussian. So how to compute the status of the Gaussian? This status suggests that that Gaussian is normal or abnormal. We maintain this information at each pass. So let's see how to compute that status. We normalize weight such that the sum is 1, and then we rank the Gaussian in decreasing order of their weight. We take top n Gaussian such that their sum of the weight becomes greater than theta normal. This is a threshold on normality, means suppose it is 0.9, means 95% of the population is normal for that targeted scenario. We label that top n Gaussian as normal, and the rest of the Gaussian are labeled as abnormal. So this way we can label the sample which is matched to any Gaussian. And the other case is that that sample is not matched to any of the Gaussian. So what to do? At that time, we see that how many Gaussians are there at that time. If number of Gaussian is up to a maximum limit, that is k, then we replace the weakest Gaussian. Otherwise, we start a new Gaussian. In both cases, we label that sample as abnormal. Let's look the experiment and results. In the first experiment, we compare the performance for low-level features as using patchwise histogram or frame-wise. We clearly see that the performance increases for patchwise emotion information. So we find
I think there's some issue with your audio, Pratibha.
Hi Pratibha, can you hear us? Hello? We cannot hear you. Pritva, sorry, we cannot hear you. Are you still there?
Hello.
Hello? Pritva, we cannot hear you. Are you speaking? No, sorry, we cannot. Okay, I think we just heard you.
Yes, you can try speaking again. Try and muting and unmuting yourself. Yes.
Yeah, Pritva, we can hear
Yes,
you
your
now.
audio is cutting
Okay.
a little bit, but you're audible.
Anyways,
Yes.
Pritva, please wrap up your presentation in next 2 minutes.
Yes. In the second diagram, we have concluded that including semantic features may further improve the performance. In here, we experiment to find the optimal event duration for our data, the 3-second best performance. With subway data, no, with our data, we have a 2-second optimum duration. And for subway data, we have the 3-second optimum duration of event. We extract the performance at each hour with our method, and we see that a performance does not degrade much. So we conclude that adaptive scene learning can be used for longer duration. We compare our approach with the standard LSTM approach and a Wang ATL, which is autoencoder based approach. The 1 hour of data is used for training in both these static approaches. And for our case, the training is done all the time. We see that our approach is outperforming both these static approaches. So we conclude that this method is adaptive. We don't need to store the video to retrain the model. We just need to store some 5-second or 3-second of data. It handles local as well as global temporal context. And since we have just k modes in the mixture, so it is maybe deleting the longer past or the events which are in transition from abnormal to normal because of the replacement policy. So that need to be tackled. And also we can explore the other multimedia information like audio and depth information. Thanks.
Thanks, Pratibha. So, do we have any questions from audience?
Adrita has one question.
Yes.
Hi Pratibha, I just wanted to understand what kind of packages have you used for temporal analysis? You said the semantic and low level information, right? The semantic, I
Yes.
understand you have used YOLO. Temporal
Yes.
analysis, what kind of packages have you used?
We have used dense optical flow standard packages available.
Okay, so in what
Yes.
form does it give the temporal information?
It gives the angle and magnitude at each pixel location in the images, and also gives the flow information, but we have not used. And yes, we have used angle and magnitude, and then compute the histogram. Like we compute the histogram on
Okay,
angle, and we
right.
have taken the weight as magnitude.
Okay, thanks Pratibha. I think that clarifies.
Yes.
Thank you.
Yes.
So, any more questions? No, I don't think there are more questions. So you can stop presenting.
Okay.
Whatever.
Yes, thank you.
Okay, thank you so much. So, do we have the next presenter with us? Any of you have?
Hello, can you hear me?
Yeah, we can hear you. Thank you. So, could you
Uh,
please share your
wait,
slides?
wait a moment.
Sure, thanks.
Uh, oh, good afternoon, everyone. I'm very happy to attend the CSIE International Conference on multimedia big data meeting online.
So could you please use your full screen if you want? Up to you.
Yes.
So could you use presentation mode? I think it would be...
Let me check.
Try clicking on the three dots below the presentation screen. There might be an option of full screen.
Yes, thanks.
Can I see my screen?
Yeah, perfect. Thanks.
Oh, can you please yes. Yes.
Wait a minute. Okay. Good afternoon, everyone. I'm very happy to attend the 6th IEE International Conference on Multimedia Big Data meeting online. I am a postgraduate from Wuhan University of Technology in China. My name is Tan Liang. You can call me Tango. The title of our paper is IMICO, study on ensemble learning of multimodal machine translation. I will introduce this paper from the following aspects. First of all, I'll give you a simple introduction about the multimodal machine translation task. The second part is about our work. Then I'll show you some experiment results and conclusions. The last part is translation results of some examples. So what's multimodal machine translation? As a translation task, which will take a source language description and translate it into target language, where this process can be supported by information from image. As this picture shows, the source language and target language are English and German. The results of machine translation with standard translation by human. Our systems are trained and tested with the multi-30 datasets provided by the workshop on machine translation organization on 2016. These datasets consist of 30K parrot sentence from training, 1,000 for validations, and 1,000 for the test set. The details of the datasets described in our paper. We use Blue to evaluate the correspondence between machine translation and professional human translation. The N equals 4. Next, I will introduce the main work of our paper. In recent years, more and more heuristic research has been done to improve translation performance by fusing different ensemble learning strategies. It's helpful to improve the performance of single model. In our paper, we propose a method of result fusion applied in the decoding process. which integrates the probabilities distribution obtained from different models to predict the next target word. As the picture shows, the details of the averaging the prediction probabilities of two models to get the greatest probabilities words. When we put the source sentence for the first word, we average the prediction probability terms of tables for the two models to get a new probability distributions. So the most probable predictions of current word is I. Then we put the prediction word I into the two submodels to obtain the probabilities distribution of the next word. By fusing model results, we get the greatest probabilities word of the next word. Repeat the above steps until the end of source sentence. Multimodal machine translation has present promising results since the incorporation of image information can enhance the model's understanding ability of text. As the first sequence transductions model, transformer has successfully applied in various translation tasks. Transformer is based on encoder-decoder structure and adopt a new attention mechanism, encoding self-attention. In our experiment, we acquired subs model by changing the number of layers, the dimension of word embedding and hidden states, and the number of multi-head and other hyperparameters to ensemble learning research. This is our framework. Especially the cooperation of image information can enhance the semantic expression of input, and it can improve the quality of MMT model on some degree. On the one hand, we process the sentence using lower casting, tokenization, and puncture normalization to improve translation quality. The test vector is the output of the transformer encoder. On the other hand, we add visual features extract from the final fully layer from the VGG19 CN as a helpful information to our MMT model. We compress the 2096 dimensions visual features related to each sentence into 512 dimension vector. Then, according to the dimension of the test mixture, the image vector is self-replicate to form an image mixture of the same dimension. With the dimension mismatch and inherent difference in content between the region and the text embedding, transformer mixture is proposed to learn the mapping. This is a gate structure combined to encoder or decoder side. The gate layer is introduced to modify the softmax prediction distribution, which can increase the probability of current answers. In our experience, by integrating encoder gate owning, decoder gate owning, and both encoder and decoder gates, the vision feature can play a role in MMT model. The following are our experimental results and conclusions. Before integrating models, we did some general optimizations. The parameter average refers to average the latest N model saved by single model at different time in the encoding phase. By average 1 to 20 checkpoint parameters of model, we found that averaging parameters based on those 20 checkpoints has a positive infection. The best result is a band update from the latest 15 checkpoints. The experimental results also show that no matter how many latest checkpoint parameters are averaged, the performance is better than the single model without parameter averaging. Furthermore, in order to add more missing semantic information without breaking structure of a sentence, we use the semantics instead of a special UNK token to replace words that do not appear in the chosen vocabulary during decoding prediction process. We use the BERT to calculate the relevant between unknown word and every word of our vocabulary list in semantic space. Then we replace the UNK token with the most relevant word. We use the following 3 ways for model integration. Fusing with same structures, different structures, and different number model. We want to increase the diversity between models to improve the translation performance by changing network structure. We double transformer layers, multi-head, and hidden states, and fuse 2 model prediction results. The results also show that the performance of transformer is sensitive to its structure, parameters, and increasing in the number of multi-head maybe has a positive impact. I think the reason is that each multi-head learns the feature in different representation space, which bring the model more learning capacity. Based on the above methods, we conduct more result fusion experiments to explore the impact of number of fusion model on translation. We fuse the results one by one from base 1 to base 8. We found that as the number of the models increase, the fusion results is gradually improved, but explicitly structure when integrate 6 models, the performance is limited. Suddenly, we got the highest blue scores in our experiment, which yields improvement of 5.12 blue points over the strong transformer baseline. The results are shown in the picture. And the different models parameters are shown in our paper. The main work of this paper is taking results fusion with parameters averaging to improve the performance of machine translation based on transformer framework. We found the ensemble learning has a positive impact on translation performance, and the best results yield improved 5 blue point over the baseline. The best results is updated from averaging the latest 15 checkpoints parameters in a single model and fusion 6 models results. Overall, we conduct extend experiments to explore the influence of hyperparameters of transformer models on the translation. We explore ensemble model to average parameters and combine results and build a more robust ensemble model based on different transformer framework. We combine multi-way of image introductions and to improve the accurement of MMT model. At the end of the presentation, I'll show you an interesting example. Look at the picture. The source language sentence is people are fixing the roof of a house. At the beginning, we use the only text-based MT sentence. The translation results means people stand on the roof, which doesn't translate the web word fixing correctly. Our MMT model with filters gets correct answer. The example that vision filters can provide more effective information to enhance the understanding of sentence semantic and improve the quality of translation sense. That's all.
Okay, thank you so much. So do we have any questions for the speaker?
I'm wondering how you integrate the probability distribution obtained from different models to predict the next target word during you training the model.
Okay. The process, the method is just when we input the source sentence, we use different models to get the probabilities of the current words. Then we got different probability distributions. As shown in this picture, model 1 got the first word. The probability is in the table. Then we average these two models result, get the final probabilities. We put the final probabilities into the two sub-models to obtain the next word probabilities. So we repeat these steps until the end of the source sentence to complete the translation.
Okay. Okay, thank you.
Any questions?
Do you use any measurement to calculate the list for each word you generated and give some score?
Yes. We get the average probabilities of one of the first word. Then we put the first word into different models encoder. The decoder of model is influenced by the performer influence.
Do you consider any weights between two models?
I can't catch your question.
Okay, so I mean, Yeah, in your example, you have two models.
Yes.
So they share the same parameters or not?
They can have same parameters. Also, they can have different parameters. We have different structures. In our fusion, we have different model. This model can maybe have same structure and the different structure. We do different structures on the fusions. And this exactly parameters are shown in our paper. Our paper has different models parameters. Can see.
Okay, thank you.
You're welcome.
Okay, any other questions? Final questions for the speaker? Okay, so someone has asked about the paper, so I just posted the link where all the papers are available, all the proceedings are available. You may have a look. And if there is not any other question, then I thanks everyone, especially the volunteers, Saksham and all others. Thank you, everyone. Thank you, Professor Yu, and thank you, Subramaniam, for all your help. And have a nice day, and probably we will meet after lunch. And looking forward to see you all after the lunch in other exciting sessions that we have very good papers. So looking forward to meet you again after the lunch. Thank you so much.
Thank you.
Bye bye.
Thank you.
Agosto